What we're going to do here is we're going to use this interactive interface and we're going to understand how vectors can be added quantitatively. If we know the direction and the magnitude numerically, we can add them with a little more precision. So what we do to use this is we just grab a vector out of the bucket and just drop it anywhere you want, and then we can do a few things. If I click anywhere along the stem of it, I can just move it, or we say translate it parallel to itself. Or if I want to turn it, I just grab the tip and I can turn it, and I can also adjust the magnitude this way. So what I want to start off with is a simple example of quantitative vector addition. So I'm gonna move this up here, make it a little more visible, and I'm gonna just say I have a 10 unit long vector, and if you look at the top here, it tells you 4 pieces of information. The absolute value of r being the resultant. That is how much the magnitude of the vector is. The angle theta is measured with respect to the x-axis. So in this case, I'm parallel to the x-axis. In other words, I have a 0-degree angle. But what would happen if I turned it 180 degrees? Would it still be a 0-degree angle? No, and so there is a distinction to make about direction. Negative x-axis, by convention, is the negative direction, so we say it's 180 degrees away from the positive x-axis. Same goes for y. Like on a graph, up is the positive direction, so that's 90 degrees from the right or the positive x. And then, as you might expect, 270 degrees, or here it says negative 90 degrees, same thing. Negative 90 meaning sort of clockwise from the positive x rather than 270 counterclockwise. So let's go back to the example. 10 unit long vector is pointing to the right, and I'm going to grab another vector over here, and I'm going to make it 20 units long. There we go. And it's also pointing with the 0-degree angle to the positive x-axis. So what happens if I want to add these together? Well, I'm going to put them tail to tip, and remember that can be done in either order, so I'll show you that it works either way. Put tail to tip like that. And then there's a few cool tools that'll show you some stuff here. So one is you can click show the sum, and that'll tell you what is the resultant, and it changes the color to green, which is nice. I'm going to just put this over the top. So now you can see, well, it's hard to tell because the tip of the green arrow is getting obscured, but I'll move it up. You can see that these are the same length, and this resultant, or the sum of the two red vectors, is equal to 20 plus 10. Of course, that isn't always true. That's only because these are parallel, meaning in the same direction. So I'm going to use the same two red vectors, except one of them is going to just turn. And actually, let's turn off that sum. I don't want to do that anymore. For no particular reason, I just want to show you you can switch back and forth. I'm going to go tail to tip the other way here. So we now have an 8 unit long vector pointing in the positive y direction and a 20 unit long vector pointing in the positive x direction. So this is where we start to get into some basic geometry and then some trigonometry as well. If I want to determine how long the resultant is, the first thing we could do is we could just grab another vector, oops, there we go, and put it from the tail of the first, put right there, and then we'll put the tip of it to the tip of the last, and it'll just tell us. So this is a 21.5 unit long vector, that's its magnitude or its size, and it makes an angle with respect to the x-axis of 21.8 degrees. Now you'll notice that even though I started with a vector along the y-axis, it's still giving me the angle 21.8 degrees with respect to the x, or horizontal. That means this 21.8 degree angle, that's here. That's between the resultant and this x component. And I want to just move these around one more time to show you that you can do it either way. So we'll go horizontal, then vertical. And notice I haven't changed this resultant. It's the same, I just moved it, which you're allowed to do. And I'm going to now just put it down, and it still fits, which is what it should do. And maybe it's more obvious now that this acute angle is 21.8 degrees. You want to get rid of a vector, you just grab it and put it in the trash, lower right-hand corner. Very Mac-like, which is nice. So I'm going to put all of them in the trash and start over. And I'm also going to change some stuff over here. So before I actually do the problem, I just want to show you what these component displays do. So the first one is going to show you tail to tail. Now I'm going to make that bigger so you know what I mean. You can add vectors like this, it's fine. It's just that tail to tip makes it a lot more obvious that the resultant is from the tail of the first to the tip of the last. And that's what style 2 does. It takes us to tail to tip. In style 3, I don't really care for, so I'm not going to show that one. So let's throw that away, and now that you know how these things work, I'm going to go back to no component display, and I'm going to bring out a new vector. If you want to take a vector, and I'm just going to grab a few of these and add it to a couple of different vectors, I want to show you how to add something that looks really complicated in a quantitative fashion. So let's say that you wanted to add these 4 vectors together. Well, in a qualitative way, that's not that hard. You just grab it and you put it tail to tip, and then you go tail to tip, and then you go tail to tip. Is that right? There it is, tail to tip. And now I'm going to go show sum. And it should fit perfectly from the beginning of the first to the end of the last. It does. I'm going to leave that intact but move it, and I'm going to just add these in a completely different order. This will work even if you add them in a different order. The order is irrelevant. There we go. And as long as I didn't screw anything up, it should fit perfectly. So the resultant of this, therefore, is 13 units long, and it makes an angle of 4.4 degrees with the horizontal, which makes sense. It looks like it's just ever so slightly above horizontal. That's all well and good because we have the software just telling us here's the angle, here's the magnitude. But what if I gave you the vectors and you had to find the angle and the magnitude instead? I'd like to stick with the notion of multiple vectors added. I'm going to make these a little different. I'm going to write down only the magnitude and the direction of each. Okay, so I'm going to add these 3 vectors together, and the first thing I want to do, we'll come over here, is I'm just going to write down the information about each one. So this first one is 12 units long, and its direction is 0 degrees. Next vector is 9.4 units long, and it makes, you know what, this looks kind of confusing. Let me put this in parentheses. 9.4 units long, and it makes an angle of 32 degrees. That means 32.0 in this case because it does go to the 10th, so I'm going to put 0.0. And then the final vector is, come here, 5.8 units long, making an angle of negative 149 degrees. So, or we could write that with respect to the positive x-axis as 211 degrees. And I'm going to do that only because I really just personally prefer always measuring from the same place and not switching. How can you add these? Well, like I told you before, you can do them qualitatively just by doing tail to tip. That's really pretty easy, and I'm going to show you that. But before I click show sum and just have the program tell us the answer, we're going to do it and then see how close we were. The way you add vectors that act in 2 dimensions like this is any vector that needs components, which again that means you have a vector that is not perfectly parallel to an axis, so 2 of these will need components, these 2 that don't make a 0 degree angle to the x. If you need components, you write down the component in each dimension, and to do that we are going to do a little bit of trigonometry. This is the one that was 9.4 units long, and it made a 32 degree angle with the x-axis, or the positive x-axis. That means the 32 degree angle is here. What we're going to do now is break it up using trigonometry. So if I know that this resultant is 9.4 units long, and I know that the angle here with the x component is 32 degrees, I'm just going to do SOHCAHTOA. So because I have the hypotenuse and I want the adjacent, we're going to use the cosine function, which equals the adjacent over the hypotenuse. We're going to now plug in the information we do have. We know the angle theta. We know x, what I wrote here was x, was 32 degrees. So we're going to say the cosine of 32, and that's in degree mode if you're using your calculator. Don't be in radians. Is equal to, let's just name this vector so we can sort of refer to all these components clearly. This is vector A. Oops, not Al. This is not vector Al. This is vector A. And its adjacent is therefore A sub x. And then the hypotenuse is the magnitude of the resultant, so it's 9.4. AX, horizontal component of this vector, is equal to 8.0. Okay, and I'm going to put that in bold to remind us that that was one of the answers we were looking for. I'm going to now do AY. Same idea, and I'm not going to walk you through SOHCAHTOA again. AY is equal to 5.0. When we do math, and the numbers are all we have to go by with a vector quantity, we use the convention that right is positive and left is negative for x, and then up is positive, down is negative for y. So even though it's redundant in mathematics, I'm going to go plus 8.0 because the x component is to the right, and plus 5.0 because the y component is to the up. To the up. Ha ha ha. It's up. We're going to now do the other vector. I'm going to call this one b. And I would like to ask that you pause and find these two components. And when you're ready, go ahead and resume. And here you have the answers. So you see why it's important to measure all angles from the same place is if you plug in the cosine and sine of 211 degrees, the calculator gives you the direction mathematically. So you should have gotten the answer in both cases was negative. In the x direction, you have a leftwards pointing component, which is consistent with this image. And in the y or vertical dimension, we have a downwards pointing component, so that should be negative as well. All right, so now here's how you add these things. You take each one and you just put the components together. So this is the horizontal component of A, the horizontal component of B, and then we'll take the horizontal component of C and we'll put it here. All right, now we're going to take the Y components, we're going to do the same thing, and you just add them. So what's 8 minus 5 plus 12? It's 15. And that is the horizontal component of the resultant. It's going to equal 15. And we just add these. 5 plus negative 3 is 2, plus 0 is just 2. The resultant is going to act in 2 dimensions. It's going to have a component in the x dimension, 15 units long, a component in the y dimension that is 2 units long. And because those are both positive, we know to go in the directions that are positive on a graph. So positive 15x is 15 to the right, positive 2y is 2 up. That is it, sort of slightly up and to the right. All right, all that remains is we have to find the angle that the resultant makes with the positive x-axis. And to do that, we're going to use trigonometry. So we're going to say that the tangent of the angle that we're looking for, we'll call that angle x, is equal to opposite 2 over adjacent 15. You will get the answer, 7.6 degrees. That is the angle the resultant makes with the positive x-axis. Last thing is to check. And finally, the resultant makes a 7.6 degree angle with the positive x-axis.